All right, we're going to be talking about two special cases as well as force polygons. So first we can define a two-force body, which is something which can be simplified to two forces acting on the body. Okay, and I'll show you what I mean here. For example, this right here is a two-force body because there are two forces on it. Okay. How about this now? Well, this is still a two-force body, even though there's three forces acting on it. These two forces, because they act at the same point, it can be simplified, like you can add this force vector up with this force vector and say those two are equivalent to just this one force vector, right? So you might get a problem where, yeah, there's a bunch of force vectors, but they all act at the same point, so it can be simplified to just a body with just two forces like this. Okay, simple enough. And so kind of the special thing about two-force bodies is in order to be in equilibrium, the line of action of both forces must be exactly the same, must have the same magnitude and opposite direction. Okay, and so if we go down here again, these two force vectors have different lines of action, right? These two force vectors, though, have the same line of action. And when I say same line of action, I don't just mean parallel to each other. I mean literally the same line, right? Like not offset, the same exact line. Okay, so if these two forces had opposite direction, like they do, or like as drawn, and they both had equal magnitude, so they were both like 5 newtons, then this body will be in equilibrium. It will have sum of forces be 0 and sum of moments be 0. Okay, you can't have a body be in equilibrium. You can't have a two-force body be in equilibrium unless all three of those conditions are met. Opposite direction, same line of action, and equal magnitude forces. Okay, and then similarly, three-force body, same thing, just can be simplified to a body where there's three forces acting on them. Now this one's a little bit different, okay? So if the body's in equilibrium, then the line of actions must intersect either at a point or be parallel. Okay. However, if a body is in equilibrium, then those things are true, right? If a body is in equilibrium, then those three forces either intersect, their line of action either intersects at a point or are all parallel to each other. Okay. However, those things being true doesn't guarantee equilibrium. So if you get a problem that says, hey, this body's in equilibrium, then automatically you know those three line of actions must intersect at a point or be parallel. But if you're given a problem where it's given to you that the line of actions of the three forces on a three-force body intersect at a point or are parallel, that does not guarantee that it's in equilibrium. Okay. So for example, this is a three-force body because their line of actions intersect at a point here. Okay. But this itself does not guarantee equilibrium. Okay. It could be, but it does not guarantee it. For example, this is 1 Newton magnitude, this is 1, and this one's like 1,000. Clearly it's not, the sum of forces aren't 0. Okay. But if you know a body's in equilibrium and it's a three-force body, then you know for a fact all three forces, their line of action, intersect at a point where all their line of actions are parallel. All right, so we're going to do an example with this. And in doing so, we'll introduce the idea of force polygons. So if we have like a bar here, right, bar here, and it has kind of like a wheel, like a roller support against a wall here, and it's pinned right here, right? Remember, pins can exert horizontal and vertical reaction forces, which is really just the same thing as some force vector, right? In any angle, any magnitude, right? So if we draw a free body diagram of the system, we have this downwards force, a horizontal force from kind of the wheel up here, and some force vector from the pin. Okay. Typically, we just draw its components, but that can also just be thought of as a singular force vector with arbitrary components that we're trying to find. Okay. Now this bar is a three-force body, right? Is three forces acting on it. And it's in equilibrium, so we know that those line of actions must intersect at a point. Okay. Now where is this point relative to this pin right here? Well, if we draw it out, right, I guess in the problem, it's given as 400 and 350. Right, just from kind of the geometry. If you have this force vector and continue it out, this force vector continuing out, this point where they must all intersect is 400 down, 350 that way. Okay. So 400, 350. So the force vector must kind of be in one of these directions, right? Its line of action must go like that. Okay. So we can find that angle right there from trig. So we get theta equals 41.186 degrees, right? So we just found the angle of that reaction force at that pin purely from knowing that all three forces must intersect at a single point. Okay, now how about the magnitude? We have specified its direction. We haven't found its magnitude yet. Okay, so if I start at the origin here, 0, 0. So the x here is like the force in the x direction. If I call vertical here, force in the y direction, we want the sum of forces to be equal to 0, right? We have a downwards force of 500, force to the left, and then some reaction. And those must all sum to 0. They're vectors. So I have downwards force of 500 newtons, and then I'm going to add to that vector a force to the left, right? That is from the roller support right here, and the force vector it creates. And then I have the reaction force at the pin that I'm going to add to that. And those three forces, 1, 2, 3, must add together and bring me back to 0. Okay, like this force vector is 500 in the negative y direction. This force vector is something in the negative x direction, and this force vector, we know its angle, right? We just found its angle. We found its angle to the horizontal, or to the vertical, to be 41.186 degrees. Okay, so these three force vectors must add together to the 0 vector. The 0 vector just being the origin, right? It has no length. Okay, so we found its direction Okay, and we're trying to find this reaction vector, its length, or its magnitude. Okay, so we can write out that cosine 41.186 degrees is equal to the adjacent side of a right triangle, so this length. So that length, which is 500 newtons, all over the magnitude of this force vector, which I'm just going to call the magnitude of the force vector at C. So that reaction force from the pin, I can solve that, and I get that magnitude is 664.38 newtons. So we just found its magnitude. Okay. Now this idea of adding force vectors kind of graphically and saying that they must add and bring you back to the origin is what a force polygon is, right? This is like a force triangle, but you could do that with, any arbitrary amount of force vectors, and they must add and bring you back to where you started, aka the origin. Okay, because the force vectors must add to the zero vector in order for a body to be in equilibrium. So we just found our answer as a vector of magnitude 664.38 and some angle 41.186 degrees. And that's our answer for our reaction force at C. We specified its magnitude and direction, in this case just graphically.